Good evening, Cawas. A pleasure to be here talking to you in person rather than via Zoom, which is the last time I gave you a talk during the days of COVID, if you remember that. So yes, this is 200 at 77. The 200-inch telescope on Mount Palomar is now 77 years old and still going strong. And this is the story of its design and its construction. Sorry. So my earliest memory of the Hale telescope is this, an image taken in 1951. No, I didn't see it in 1951. Perhaps the 1970s. I seem to remember that I was at school, went to a school library at lunchtime, opened the Atlas of the Universe and saw many wonderful images, including this one. And this image, this photograph, more than any other, is probably the one that got me interested in astronomy back in the 1970s. I looked at this and I thought, wow, there are really amazing things out in the universe. What is this? Why is it the shape of a chess piece? What's it made of? How come it looks like that? And so that got me on this long journey of wanting to look out into the heavens and try and understand how the universe works. So this talk is a little bit about George Ellery Hale, only as an introduction, as the man who ultimately produced the largest telescopes in the world, 40-inch, 60-inch, 100-inch, and this one is, of course, about the 200-inch telescope. I'll be looking at how they selected a site, how they made the mirror, and how they made the telescope. And then I'll say a little bit about what it's doing now, 77 years after first light of the Hale telescope. And then I'll summarize and acknowledge where I got all of this material, including the prints that you can see laid out on the table at the front here. So George Ellery Hale was an amazing man. He was known for his work in solar astronomy, and he was a co-inventor of the spectrohelioscope that allowed you to take images of the sun at different wavelengths. But he's really known for the fact that not once, not twice, but 3 times he built the largest telescope in the world. He started by overseeing the project of the 40-inch refractor in Yerkes Observatory, still the largest working refractor in the world. And then, as director of the Mount Wilson Observatory, he oversaw the 60-inch telescope and then the 100-inch Hooker telescope, which was finished in 1918. But almost as soon as the Hooker was done and started taking observations, he thought, what next? After making those 3, or seeing through those 3 telescopes, he then said, we need to go bigger. Notice the transition, 40-inch, half as much again, 60-inch, half as much again, roughly speaking, 100-inch. So the next logical step would be to build a 150-inch objective or mirror, giving you twice the collecting area. But Hale thought, no, let's not do it incrementally. Let's make a really big jump and go to double the diameter, 4 times the collecting area. He realized that light, the amount of light you can collect, is absolutely critical. So let's go big or go home. Let's try and make a 200-inch telescope. It took him a long time to find the funding. He was a billionaire whisperer. He would talk to people with money and try and convince them to give him the money for his projects. In 1928, he approached the Rockefeller Foundation and persuaded them to cough up $6 million. This is the 1920s, remember? Inflation has, gone a long way since then. So 6 million in 1920s would be, of course, many tens as much in modern accounting. He got them to put the whole money on the table, not just the money to build the telescope with the mirror, not just the telescope and the dome, not just the telescope and the dome, but the entire observatory, which didn't exist at the time, was funded by the Rockefeller Foundation. So having got the funding, what's the next decision? Well, where are you going to put this new observatory? Hale said, well, there are various places in the world we can put it, but of course the most important place in the world is California, and all of the important astronomers in the world are based in Los Angeles, as was well known. You can argue that if you wish. But he believed it was a good idea to stay close to home. Rather than put this new observatory on the other side of the world, where it would be difficult to keep an eye on it, he decided to put it in his own beloved state of California. So there's Los Angeles. And the Mount Wilson Observatory is in the mountains just to the north of Los Angeles. But of course, the city of Los Angeles was growing year by year. Not only was it starting to impinge on Mount Wilson, but also San Fernando and San Bernardino were starting to envelop Mount Wilson, and therefore there was that light pollution on essentially all fronts, the south and the southwest and the southeast. So it was realized that Mount Wilson was not the best place to put a new telescope, even though that was considered a good place when the Hooker telescope was positioned there some years earlier. So he sent out scouting parties to various mountains in Southern California, looking for a good site. They found half a dozen sites shortlisted as sites with good astronomical seeing. He then thought he would check with one of his colleagues at Caltech. Let's just make sure that these are sensible places to put a telescope. He checked with his colleague in the geology section, a certain Professor Richter, yes, Richter of the Richter scale, and said, any of these sites good or bad choices? Richter said, that one is not a good one. Why? Because it's on the San Andreas Fault, not a good place to put a telescope. But there is one place on your shortlist that I think is definitely worth thinking about, Palomar Mountain. Palomar Mountain is a slab of granite, 30 miles long, 10 miles wide, 25 miles deep. It is trillions upon trillions of tons of granite. If California has an earthquake, that is not going anywhere. So if you build your telescope on that mountain and put some nice good footings down into the granite, you will be fine. So it was decided to go with Palomar Mountain. Yes, there is a little village to its south called San Diego. That's grown a little bit as well. But that was considered far enough away. You can see the scale there, 20 miles. So San Diego was something like 60 miles away to the south. And that was considered far enough away that it wouldn't impinge on the nice dark skies of Palomar Mountain. So they have the money, and they've now decided where to put it. That's what Palomar Mountain looks like now, or at least looked like a few years back. A rather beautiful site, and I visited it back in 1982 when I was a student. Slightly longer hair there, I think. And it's difficult to realize when you look at a picture like that, when you're walking around in shirt sleeves. That was during the summer months, but it can get very cold in the winter. And at this altitude, 1,700 meters or so, 6,000 feet, you basically have to pay people to shovel snow off the roof in order that the dome doesn't get too heavy with all of the snowfall. So it is something you have to worry about. 6,000 feet, and remember, this is effectively a virgin site as far as an astronomical observatory is concerned. No infrastructure whatsoever. So not only have you got to build a telescope and a dome, you've got to build the rest of the observatory, and everything goes up that road in order to get to the top, where you then have to start building particular buildings and all of the infrastructure you need. So they knew it was going to be tough, but they decided that this was the best place to do it, not that many miles from home base, as it were, in Los Angeles. So having got the funding, having decided where it's going to go, you have to then design yourself a telescope, and you have to think, well, this is going to be the largest telescope in the world by far. It's going to be a mirror 4 times bigger than the world's largest as it stands at the moment. So how are we going to mount this huge telescope? As amateur astronomers, we know that we have a few choices. For instance, we have a German mount which has a counterweight, or we can fork mount, or not so popular these days, an English yoke mount, which is effectively a fork supported from both ends, and that gives you enormous stability even for very heavy loads. So yoke mounting was popular when you have a large mass to move around. And it's interesting to note that the 3 previous telescopes, each of which was the largest in the world at the time they were built, follow each of these 3 designs. The Yerkes Observatory telescope, the 40-inch, was a German mount, and the 60-inch was a fork mount, and the 100-inch Hooker was on a yoke mount. Yet I realise the 60-inch doesn't really look like a fork mount, mainly because the forks are rather stubby because of the centre of mass being fairly close to the mirror. But they are 3 different designs. But one thing we can note with the hooker is because it's in a yoke mount, notice that just like in the drawing there, the telescope itself can't point to the North Pole. Even if the tube was shorter, such that it didn't actually clang into the yoke mount, it still would only be looking at the North Polar bearing. It wouldn't be able to look at the North Polar sky. And when it came to building the 200-inch, Hale was determined that the new telescope, the 200-inch telescope, would not suffer from the same limitations as the hooker telescope. So one, I've just mentioned, the English or the yoke mounting that was popular at the time meant that in the case of the hooker, it couldn't make any observations within 30 degrees of the pole. So there was quite a large patch of sky that it would never be able to observe. The second limitation was the fact that the mirror in the hooker telescope was made from plate glass. And plate glass will expand and contract quite substantially as the temperature varies. And with the hooker telescope, that meant that, for instance, if the nighttime temperature was a couple of degrees different to what they were expecting it to be, they would have to wait until the mirror adopted the same temperature as the surrounding ambient air, because otherwise, as the temperatures changed, the plate glass would expand or contract if it was cooling down, and distortions in the plate glass would mean that you can't assume that the figure of the mirror is correct until it's reached equilibrium. And that could take a substantial length of time with plate glass. It could take hours. In some cases, the hooker telescope was not actually usable for half of the night until it finally got until the early hours of the morning, when the temperature stabilized and the mirror then adopted the correct figure. Hale did not want to have those same limitations with the 200-inch. So firstly, what did he do about the fact that the yoke mounting avoids the pole, or stops you looking at the pole? The first choice was, let's go for a yoke mounting, but let's have the north end of the yoke, not like the south end where it just has a simple bearing. Let's make the north mounting of the yoke a horseshoe. And because it's a horseshoe, that means if you want to, you can swing the telescope in declination all the way to declination plus 90, at which point it just nestles in the middle of the horseshoe. So you're not limited to any part of sky. Yes, of course, there will be some constellations in the north. You have to wait for the right time of year. But basically, it can cover any declination from plus 90 all the way to the southern horizon. So that's how they got around that particular limitation of the hooker. But what about the limitation of the mirror? This is what the 100-inch hooker mirror looks like seen from the side. We're looking into the glass. There's the aluminized surface right at the top. And looking into the side of the mirror, we can see it's laminated with different layers, implying that when the glass was poured to make this particular glass slab, it looks like parts of it solidified before the next part was poured in, etc. And you'll notice there are thousands upon thousands upon thousands of air bubbles. Air expands and contracts at different rate to glass. So again, whenever you have any temperature variations, you would have to wait for a long, long time for this mirror to come into equilibrium. You can't start observing while it's still contracting or expanding if it's cooling down or warming up. If you start with the 100-inch mirror as a start and say, can we simply scale this up to make a 200-inch mirror? Well, part of the problem is not only that you still have these problems, part of the problem is the length of time it would take to actually cool from the melt, for instance. If you had a glass plate, it would be a huge amount of mass. The mass in the hooker mirror is about 5 tons. If you scale that up to twice the diameter, 4 times the area, twice the thickness, you end up with a mirror that's some 8 times the mass. So the 2 things can be done. One is you don't use plate glass, you use low expansion glass, we would call it Pyrex, a borosilicate glass. And the other one is, in order to not have a mirror that's 8 times the mass, you would actually have to find some way of making a mirror in which you had the area that you want and the stiffness and the rigidity that you want, but not the mass that's 8 times as much, despite being 4 times the area. So they had to come up with different ways of making mirrors. So Hale, after a few blind alleys, went to the Corning Glass Works on the East Coast and said, how are we going to do this? They said, no problem, in the sense that we've been making ovenware for ages. We make Pyrex custard jugs. I'm sure we can make a 200-inch mirror for you. Okay, it took a little bit of time, but that was this partnership between Hale specifying what he wanted and Corning Glass Works saying what was physically possible. So this is how a mirror is normally made. You start with a mold and you pour molten glass in and it fills up until you have effectively a pancake of whatever diameter the mold will allow and whatever thickness you think is appropriate for the stiffness of the mirror you want. So you pour it in and then you let it solidify by cooling down. With a plate glass mirror like the Hooker, it would take many months to cool down. But if you make a mirror that's much larger, getting heat out of the middle of the mirror, because of course the heat would be lost from the surfaces, that means it would take an awful lot longer. They calculated that if we use this way of making a mirror, by simply making a pancake, and then once it's cooled down to room temperature, we start grinding away the top and coat it with a metal to make our reflecting surface. If we simply scale up the idea of taking a 100-inch and scale it up to 8 times the mass, how long would it be before you could cool from the molten glass, something like 1500 Celsius, down to room temperature? You would have to cool it slowly enough not to introduce any stresses in the glass. It was calculated with a mirror 8 times the mass of the Hooker. The length of time it would take to cool down to room temperature would be approximately 10 years. Not really feasible. They had to find a better way of doing it. So they said, let's figure out how we can make the mass of the mirror less so that we can cool it in, let's say, less than a year and not produce any stresses in the glass. So they came up with this idea of putting fire bricks in the mold. Then you pour glass in and the glass fills up. The fire bricks are effectively just insulators. They are called cores. They effectively are just material that allows the glass to flow around them. And so we end up with a mirror that is the same thickness, but once we've cooled it down and taken the cores out, we can then grind away the top surface just as we did before and generate the curve just as we did before. But now we've got a mirror with much lower mass. We have now removed, effectively they're just air gaps now that we've removed the fire bricks, and we're left with ribs of glass. So this is just as rigid as it would be if it was a solid, but it's now a lot lighter. So instead of having a 40-ton mirror, which is what it would be if we simply scaled up the Hooker, we now have something like a 20-ton mirror, and it'll be a little less once we've ground it to the right shape. So we have a mirror with the surface as before, but now it's very light and very strong. This is what it actually looks like, the mold itself. These are the fire bricks that have been placed in the mold, and this is what the glass is going to move around, and the glass is going to flow in the channels between these fire bricks, and that is what's going to give the ribbed structure that we're about to see. Let's see how it was actually done in practice. I realize you can't read this because the text is too small, but this is how the Corning Glass Works worked. They had a large oven here with the mold, and these teams of people with these large ice cream scoops. Okay, they're not ice cream scoops, they're large ladles for carrying glass around, but effectively there's a large tank at the end there with something like 60 tons of molten glass. They scoop out the molten glass from the tank and then carry it over to the mold, and as you can see on the team on the left-hand side, pour it into the mold. And they would have to do this hundreds of times in order to get something like 20 tons of liquid glass into the mold, and then once that's complete, they would then take the best part of a year to cool it down to room temperature, and then hopefully they've got the mirror that they want. So let's see these teams of people with their ice cream scoops in action. There they are, an ice cream scoop is going into the tank on the right. They now need to counterbalance it. Everybody jump on the end and then pull it out. And there we have some molten glass. Water is being sprayed onto the ladle so that the ladles don't melt. And here it is again from a different angle. In goes the scoop. It's dipped into the tank, turned around, Everybody jumps on the right-hand end, and out it comes, dripping with molten glass. You scrape away the molten glass that's excess. You get somebody with water to spray water onto the ladle, again here, to avoid the ladle melting. And then you take the ladle over to the mold, and in the right place, you dump your 100 kilograms of glass into the oven there, pouring it into the mold. Any glass that's left over, you then tip into a wheelbarrow, and then you take the wheelbarrow back to the tank and recycle it for the next batch, as it were. And you do that something like 100 or 200 times until you've got your 20 tons of glass in the mold. So that's a static shot, a publicity shot from Corning Museum of Glass showing how it was done. You can see most of the weight is actually taken by this overhead rail system, and the people are there to try and make sure that the glass is put into the right part of the mold to try and get a continuous fill of your 20 tons of glass. There it is, again, seen from the team there, of it being poured in. I presume that's a supervisor on the left-hand side because he's wearing a hat. You can see also that the ovens are made of fire bricks. Unfortunately, some of the fire bricks in the mold itself came loose, and fire bricks are less dense than glass, so they pop to the surface. Also, some bricks on the inside of the oven fell during the time that the mirror was being made, and that meant you ended up with an absolute mess in the surface of your mirror. By the time you've taken these loose fire bricks out, ones that have popped loose from the mold or ones that have fallen in from the oven, you end up with huge gouges in the surface of your mirror. They did think for a little while, well, we've got to actually grind this mirror down. How much are we actually going to remove? They calculated that they'd probably end up removing about 5 tons of dust by grinding it to the right shape. But unfortunately, it would be so deep, the actual gouges were so deep that even taking 5 tons off the surface would not clear those gouges. So that was declared a failure, but they figured this is what we need to do. We need to make sure that those individual fire bricks are absolutely solidly bolted down in the mold, and we need to make sure the oven doesn't have any loose bricks that could possibly fall into the mirror during its slow cool from 1500 Celsius down to room temperature. So they learned from their mistake, and the following year, 1935, they had a successful casting of the mirror, and this is what it ends up looking like. We're now looking at the back of the mirror, and you can see very clearly the ribbed structure that results of having lots of fire bricks in the mold, which then get removed. There were all sorts of problems, but this particular publicity shot shows you, A, how big the hole in the middle is. For those that know their telescopes, a Cassegrain mirror needs a hole in the middle for the light to come through. So that's a Cassegrain orifice there, about 1 meter or so in diameter. And again, it gives you a very clear view of the ribbed structure that results from having lots of fire bricks in the mold. Some of the fire bricks were sort of hexagonal shaped. Some of them were circular, because these circular holes here are where the mirror support system is going to make sure that the mirror is supported to make sure it doesn't flex when it's actually in use. So they had various problems with the first casting. Even the second casting had some problems. They had a flood of the neighboring river. The river was going to hit the transformers, which were feeding power to the ovens to keep the mirror warm. They had to make a decision. Are we going to kill the power, or are we going to let the river hit live transformers? That's a hell of a decision that you have to make. They also had a little bit of an earthquake as well, but they got round all of these problems, and the second mirror was declared a success. This is it being shipped over from the East Coast now to Caltech on the West Coast. There's 20 tons of mirror hanging on a strap as they move it around. You can see the thickness of the mirror, about 0.5 meter or so. And again, you see the translucence of the mirror because it's relatively thin at this point. Again, you see the ribbed structure very clearly at the back there. Once it was in Caltech, now you've got to grind it to the right shape. You've got a mirror that's been cooled from its molten state to room temperature in about a year, but it's going to take you quite a while to grind that mirror to the right shape. The team was something like 21 men, no women at the time. and it took them a total of 11 years to grind the mirror. Now that's a little longer than it should take for reasons that we'll come to in just a few slides' time. But that's the team standing in front of the mirror. The mirror itself was put onto a turntable, and then a polishing and grinding tool was moved backwards and forwards on this gantry, which moved backwards and forwards. So the idea is you start grinding it to the right shape, and every once in a while you need to test whether or not the shape is, roughly speaking, where you want it to be. And then you make smaller and smaller and smaller changes to the surface until you get the surface you want. The only real way of testing it in this optics shop was to actually turn the whole thing. The turntable itself, perhaps you can almost see, is actually pivoted. So this entire thing, once they've stopped turning it, can be pivoted so it points horizontally. So the mirror is now vertical. And here we come to the crux of it is absolutely imperative that you support these mirrors correctly. If you're grinding it while it's horizontal, but testing it while it's vertical, you have to be absolutely sure that the mirror is not sagging or slumping. You have to make sure that those mirror supports, which go in the circular areas in the back of the mirror, are doing their job to absolutely support the mirror and provide exactly the right force to make sure that the mirror doesn't have any stresses which are going to distort the surface of the mirror. Those mirror supports are a marvel of engineering in their own right, and it's not something I've got time to talk about, but there are images of it on the drawings on the front here. This guy at the front is not doing the hoovering. He is using an electromagnet to pick up any tiny shards of metal which might be on the floor to make sure they don't end up going into the grinding machine. Despite that, I still find it very odd that people are there with pipes. I think that means it's an affectation. I don't think tobacco was actually allowed in the optics shop, but people still prefer to have a pipe clenched between their teeth because it made them feel better. Every once in a while, they would do this test, put the mirror vertical, and then do a knife edge test to make sure that they were grinding the surface to the correct shape, so-called figuring it. And here we can see a person actually doing the knife edge test. There he is, a little bit larger. At the same time the mirror was being worked on, they were also working on the engineering of let's get the observatory building itself done. So remember, you're on top of a slab of granite, so all you need to do is to make some holes in the granite, and there's your absolutely solid foundation for your observatory and your telescope. So this is in the mid-30s, it's starting to take shape there. The walls aren't particularly high compared to the overall size of the observatory. Once you reach about that height, you have to lay down the track of the dome, which is going to rotate to, of course, allow the telescope to see various parts of sky. When asked, well, how smooth do you want the rails there on this observatory? Hale said something like, 1/1000th of an inch ought to do, that's no problem. So they basically tried to grind the rails, the double rail on which the dome sits. Hale specified that when the dome moves, and the dome, by the way, is about 1,000 tons, when the dome moves, there shouldn't be any vibration carried to the telescope whatsoever. So if the dome is moving, the telescope can still do its job. So once the tracks were finished, then they could start building the dome itself. And by 1937, it actually starts to look like an observatory. You get a feeling for how that's all going. In this particular talk, I'm using the wonderful work of Russell Porter to actually illustrate some of the goings-on in the telescope and in the observatory. Again, some of the prints are here in front of us. This one in particular is a wonderful cross-section of the whole observatory as well as the telescope, showing ghost images of what it's like when it's pointing towards the pole or what it's like when it's pointing towards the gantry that allows observers into the prime focus cage right at the top there. So let's use this as a way of just getting a feel for how the telescope is put together in this rather wonderful cross-section. So let's just fade it out slightly so we can see a little more clearly. There's the mirror. I haven't attempted to show the correct figure of the mirror. Let's just have it as a glass slab. Prime focus means the light hits the mirror and ends up in the prime focus cage. This large cylinder, the top half of which can take an observer or two, and the bottom half of which contains various mirrors. So if you want to use the telescope at prime focus with the shortest focal length, the 5-meter mirror, it's roughly f3.3, then you get a wide field of view for your photographic plate up here. But for a lot of situations, you don't necessarily want a wide field of view. You want a lot of detail, perhaps in a relatively small feature, a relatively small galaxy, for instance. So you might want a longer focal length. So mirrors in the bottom half of the prime focus cage would fold down. So for instance, a Cassegrain mirror would fold down as a secondary there, and then the light would hit the primary, then the secondary, then go through a hole in the primary. I haven't shown it in this diagram, and then you would come to focus below the main mirror cell. The advantage here is that not only do you have a longer focal length, f15 or so rather than f3, you can also put a lot of equipment here without upsetting the balance of the telescope too much. It was estimated that you could probably put about a ton of equipment behind the mirror cell and it would still be relatively happy. If that wasn't enough for you, you can alternatively put a third mirror at the intersection of the declination and the polar axes, and that would mean that the light hits the primary, then the secondary, and then the tertiary mirror and gets sent down the polar axis itself. And there's a room which is situated at the end of the polar axis. There's a sort of a token individual to show you there. The point being that that focal point does not change. It doesn't matter where the telescope is pointing in the sky. It doesn't matter that it's tracking. It doesn't matter if it changes declination. That focal point stays absolutely fixed. And therefore, you can put really heavy equipment there that doesn't have to move at all. You can put spectroscopes, for instance. And so quite a lot of spectroscopic equipment was placed down at that particular so-called coude focus. There's an indication of how the thing was put together. The actual steel work, not the mirror, but the steel work was put together at Westinghouse over on the East Coast in Philadelphia. That gives you an idea of the size of the base ring of the telescope with some of the workers that were responsible for the steel work and some of the welding. Again, a few random pieces of steel work here, part of the enormous horseshoe, part of the telescope truss itself, part of one of the bearings, etc. It took a few years to, of course, carry out all of this work, partly because, as was once described, putting this together is like building a battleship, but with the precision of a Swiss watch. It's not just a question of let's just make it as best we can. Hale insisted on precision to make the best possible instrument he could. This is basically the topping out of when all of the steel work was ready. They then had to effectively dismantle bits of it and ship it over to the West Coast from the East Coast. You possibly can't see, but this is Professor Einstein here in the gallery, one of the dignitaries. He was particularly interested, as a theorist, he wasn't interested in observing, but he was interested in knowing whether or not a telescope like this, when it was operational, would be able to see the most distant galaxies, and it might be a critical test of his general theory of relativity. So he's very interested in the results coming out of this telescope. It is said that Mrs. Einstein was there as well and asked, well, what's this telescope for then? And she was told, well, this telescope will look out into the universe and see galaxies and study the universe, and we'll be able to know how the universe came to be and how it's evolving and why it's evolving the way it is. She was not impressed with that. She said, my husband can do that on the back of an envelope. The engineering itself was quite incredible. That's part of the horseshoe, effectively the inside of the horseshoe. The outside edges of the horseshoe are 4-inch thick slabs of steel, 4.5-inch thick plates of steel, which were bent in a forge press, which provided something like 12,000 tons of force to bend the steel, even though it's 4.5 inches thick, into these curves. And there you see a publicity shot, because there's not much point measuring it once it's like this, because it's built, so you can't really unbuild it. But basically, that's what the horseshoe looked like. It was made in 3 pieces, not because they couldn't build it in one piece, but because once it was finished, they had to get it from the East Coast to the West Coast. That means putting it on a train. And therefore, each piece had to be small enough to go onto a train and miss any tunnels or bridges that were on the way. So it was made in 3 pieces. The outer edge is the bearing surface. This is what provides the precision of the motion, the polar axis, and hence the right ascension drive of the telescope. So that had to be machined, not with these lugs, they were just there to move the thing around. Once those lugs were removed, it had to be machined to very high precision. We're talking a fraction of a thousandth of an inch or maybe a few microns precision of the actual surface. And then it was unbolted and shipped out. The other end, the south end of the bearing, the horseshoe is the north end. The south end looks a little bit like a telephone handset. Remember, it's a yoke mounting, so there were two large cylinders holding the telescope going from the south end to the north end, and the ends of the cylinders go into these slots here, and the south bearing itself is in that central hole. So yes, it does look like a rather large telephone handset, but that's the south part of the yoke, which eventually was coupled up with these tubes, which are the yoke themselves, and then the horseshoe goes on this end. Notice the size. Each of these is easily large enough to take a man. Well, it sort of has to be that way because the declination motors sit inside one of these arms, and therefore you have to be able to get in there to actually check everything is okay. So yes, there has to be access from this end inside the yoke arms themselves. And as I say, once all of the bits were made, they had to be taken over to California on a train and taken up that grade. Remember that grade? That twisty road that gets you from low to eventually 6,000 feet. Not only the telescope and the mirror, but also every piece that's going to be building your observatory. Every piece of steel going up there has to go up that road. So it was quite a feat. Perhaps you noticed the firm doing it. Hazard and Sons. So in this particular case, it looks to me like the middle bit of the horseshoe that's going up. 2 trucks at the front pulling and 1 truck at the back pushing, and hopefully you can get it up that grade without any of these bits falling off the side and tumbling down the side of the mountain. As far as I know, they didn't lose anything. Everything worked according to plan. As they arrived at the observatory, they came in at ground level and then went up through a hole in the observatory floor. So this is the observatory floor itself. And each piece here, it's the south yoke coming in. Each piece was brought in, and then effectively the entire thing was reassembled. So as it comes in, there's part of the telescope tube itself. Here's part of the horseshoe coming in. Looks like part of the yoke down at the bottom there came in a little earlier. As each piece arrives, you start bolting it all together. If you're missing it, there's a person standing right at the front there to give you a reminder of the scale. And as another reminder, who cares about health and safety? No harnesses, no hard hats. People just clambered over the ironwork. Remember, this is how you build the Empire State Building. You just walk up and down the girders. You don't worry about health and safety or anything like that. If anybody insisted on somebody wearing a hat, well, it was probably a fedora rather than a hard hat. So here somebody is inspecting the prime focus cage. The top half of the prime focus cage where the observer might sit, and the bottom half is where the mirrors would fold down if you wanted a Cassegrain focus or a Coude focus. As it was being put together, they figured, let's just make sure it moves the way it ought to. So here they are actually driving the telescope towards the south. These people here, I guess they're engineers because they've got their sleeves rolled up. So they're just checking that the telescope can point to the southern horizon. It would never actually do so because you never point a telescope that low on the horizon, and San Diego is over there anyway. But they're just checking that if you are going to drive the telescope, does everything work the way it should? So just making sure that there's no horrible noises as they start to drive the telescope down to the horizon. What sort of accuracy do you want to be able to point this telescope to? Hale had very clear ideas on that as well. Well, it's a 500-ton telescope, so let's say we want a go-to accuracy of 1 arcsecond. That's a fairly amazing thing to ask. And the question is, well, how accurately do you need to grind the gears in order to be able to point that size telescope to an accuracy of order arcsecond? That's what the right ascension gear looked like. It weighed about 10 tons. The declination gear was about the same. Again, man with hat. There's always men with hats around. If they haven't got pipes, they've got hats. It gives you an idea of scale. 10 tons of right ascension gear, and the precision with which they had to cut the individual teeth in order to make sure that the final pointing accuracy was something that they could measure in arc seconds, preferably no worse than a couple of arc seconds, was quite incredible in itself. They were not only in the optics shop trying to grind the surface of the mirror to an accuracy of something like 1/20th of a wavelength, they had the task here of grinding the teeth on the gear wheels to an accuracy of better than 1/1000th of an inch, basically just a couple of microns or so. So this is one of the gears being checked. They had to A, do the grinding and then do the polishing of the teeth to the accuracy needed. So they would grind the teeth. This would take years, by the way. This is not a fast process. They would grind the individual teeth by these grinders, and then they would switch to polishing, which looks very similar, but the teeth have now changed shape slightly, and they've got polishing solution in between. How do you know when you've got the polishing just right? How do you know when you've got the precision you need? Well, you get an expert in. A man with a pipe runs his finger over the individual teeth and checks that they are as smooth as they can be. The precision with which you can move your finger and tell whether or not there's something wrong is quite phenomenal. So yes, they had experts who could say that, yep, these gear teeth have been made to the precision that we can possibly achieve, and then the worm wheel and the worm gear are then declared as finished and ready to move the telescope. How big a motor do you need to do that? Remember, we're trying to move 500 tons of telescope plus yoke plus horseshoe. It takes a huge motor to do that. You can get the idea of the scale here. Yep, it's tiny. A motor of something like 1/12th of a horsepower was enough to actually move this thing. Even if you wanted to slew it quickly, you would only need a few horsepower to move the entire system. The friction, because it was on oil bearings, not roller bearings, not ball bearings, it was on oil pads, the friction was so low, they actually had a problem with the friction being too low and had to artificially increase it to make sure that it worked to spec. So Russell Porter, the author and the designer of these various prints that we can see on the front table, he was doing a lot of drawings between 1937 and 1940 before the telescope actually existed as such. And by looking at blueprints of what things were supposed to look like, he would figure out in 3 dimensions in his head what it would look like when it's complete if you had a cutaway section. And that's why these individual drawings are so amazing. I'm not going to go through them all because it would take all night to discuss each one in detail, but some of them are truly remarkable. There's the right ascension drive here, and in front of this man at the bottom left is an analog computer that was designed such that not only can you point with the precision that you need into the sky, you can even take into account the fact that a star isn't where it should be because of refraction through the Earth's atmosphere. That might only be a shift of arc seconds, but you can calculate what that refractive shift is, and you can program it into the cams and levers of an analog computer. Amazing ideas. That's what's going on inside one of the yoke arms, the hollow tubes, the declination drive. You can get the scale from the person standing next to the drive. So the motor is driving through to this large declination wheel in the background, and there's the telescope tube sitting over to the right-hand side there. This is what it looks like if you were looking into the prime focus cage. That's how you get into the prime focus cage. The telescope would be moved until it was not quite horizontal, and then an astronomer would get into this gantry, open a gate, and climb into the telescope prime focus cage. I'm told that the control system had a man overboard button, just in case they ever fell out, but I'm not sure they ever actually used that. This is what it would look like, perhaps, for an astronomer sitting at the top half of the prime focus cage at the so-called pedestal, where the light comes up for prime focus, and there you could have a photographic plate if you wanted to get, for instance, an image with the widest possible angle, rather than the longer focal lengths of Cassegrain or Coude focus. So, is it finished? Everybody thought that, yeah, we're pretty much there. The telescope tube looks like it's complete and everything is working and everything is driving and everything moves the way it should. The mirror has been ground to within a few millionths of an inch of the correct shape, starting with a sphere and then ending up with a parabola. Everything looks like it is absolutely on schedule. But it's 1941. Pearl Harbor brings the Americans into World War II, and that effectively shuts down the effort of the machine shops and the optics shops as well. So everything had to be mothballed for quite a few years, and it took until, of course, 1945 before they started to get everything back on track again. So now you can see the state of the mirror. Perhaps you can see that the mirror now has a little bit of a dish shape to it. You can just about see that there. Notice that the pipes have gone. I'm not sure that's a decision. Not only are the pipes gone, but we now have some women on the team, which is excellent to see. There's a limit to how much testing you can do in the optics laboratory. Yes, you can move the mirror and you can do knife edge tests and you can check the mirror appears to be focusing the way you want it to and appears to be essentially perfect. But the only way to be absolutely sure is to test it on a star. So at that point, they took it up the road in this package here, in this crate, and dedicated the telescope. So this is now 1948, the dedication ceremony. So this is the point at which the 200-inch telescope became the Hale telescope. It was dedicated in Hale's memory, who unfortunately had died some years earlier. So he never actually got to see the final result and the final first light of his telescope. You realize the size of the observatory when you realize that there were something like 1,000 people at the dedication ceremony itself. In the background is the vacuum chamber in which they re-illuminized the mirror. And at this particular point, there's no mirror in the system. There's just a dummy there just to make sure everything is counterbalanced correctly. But the mirror came up from the optics shop, and they put it onto the back end of the telescope, looked at a star, and tried to determine whether the mirror was perfect or not. And generally speaking, you wouldn't expect it to be, from a laboratory to actually testing it on a star. They figured out which parts of the mirror weren't quite right. They might have got it to a fraction of a wavelength. Maybe they've got it to an eighth of a wavelength or a tenth, but they wanted it to a 20th of a wavelength across the entire 5 meters. So they made a note of which particular places it was just a little bit too high. So these aren't dust specks or bits of confetti. These are areas where the master polisher was told this bit is a few millionths too high, that bit is a few millionths too high. And he would go over and, without using a grinding machine, but just using effectively a cloth and a little bit of, in some cases, something as innocuous as jeweler's rouge, just literally try and take a few millionths of an inch off to try and get that shape correct. There's no need for silvering at this point because you're just checking the figure of the mirror. So that would come off, he would redo the figuring, it would go back on the telescope, look at a star, try and figure out if there were still some high points on any part of the mirror, take it off again, check it, take a few millionths off, put it back, and after a few backwards and forwards, they finally declared that now it is perfect and now we can adopt a aluminium surface, we can vaporize some aluminium in the vacuum chamber and put down an aluminium surface and put the mirror in and use it for real. So that's what it looks like with an astronomer in the prime focus cage. There's the gantry that allows you to get in and out. There's a reminder of what Russell Porter's drawings looked like with an astronomer at the top there. Edwin Hubble was very interested, having spent a lot of time on the Hooker telescope trying to determine the recession velocity of galaxies. He was very interested in using the Hale to actually see further into the distance. I'm sure because the cage at the end there is open to the elements, it would get very cold. Remember the snow on the dome roof? It would get very cold during the winter, and so I'm sure they were very appreciative of the war surplus of having heated flying suits to keep the astronomers warm whilst doing their stuff in the prime focus cage. Here we get an idea of what an observing session might have been like. Here an observer is going to place a plate holder, a photographic plate holder, onto the top of the pedestal at the prime focus of the Hale. In goes the plate holder, and that's locked into place. And then the plate goes in. Hey, whoa, 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 no, that's not the plate. Put that back. Yeah, we want the box at the end there. Yeah, that's the one. Yeah, okay. The box at the end contains the photographic plate, so this would come out in the dark, of course, and would go into that position. Then the back of, yeah, he's got it now. Then the back of the plate holder goes on, and that locks the plate into position, nice and firmly, at the focus of the main primary mirror. Once everything is in place, you would then choose a guide star, so there's a little guide telescope on the left-hand side there. You would then find yourself a suitable guide star and put it in the middle of crosshairs and use that as a way of checking that the telescope is tracking the way you hope it is. Once you've identified your guide star, you can then say, right, I'm nearly ready. Just make sure I've got my sandwiches. Yep, peanut butter, excellent. Okay, we're ready to go. We can now start the exposure and then we can basically say we're off. And every once in a while, just check the guide star to make sure everything is tracking perfectly. You can't be absolutely sure there isn't, for instance, the astronomer just shifting his weight slightly, producing tiny sub-arc second changes to the position, so you can always just make manual adjustments. And this comes back to the original photograph. First light was 1949. First light 1949 means it's 77 years old from first light to today. And that picture was taken a couple of years later. So this picture is 3/4 of a century old. And again, it comes back to one of the first images that I saw, wondering what on earth is going on in the universe that ends up with structures like that. I haven't got time to talk about all of the advances that the Hale telescope has provided in terms of our understanding. It has imaged so many objects within the Milky Way, so many galaxies out there in the universe during the 1950s, 60s, 70s, etc., right up to the present day. And it is still doing useful work. It's no longer the largest telescope in the world. It was overtaken in the 1990s by the Keck's. But it is still producing useful data because it is being used as a test bed. It is such a fantastic 5-meter mirror. Okay, it's only half the size of something like the Keck telescopes, but it is still large enough that it collects a lot of light and can be used as a test bed. So for instance, back in 2013, it was used as a test bed to see how well adaptive optics could work. We know that ground-based telescopes will suffer because of turbulence of the Earth's atmosphere. But computers these days can look at the turbulence, look at the effect of the turbulence, and modify the wavefront on the mirrors such that you effectively distort the mirrors to compensate for the turbulence of the atmosphere, and you end up with sharp images. So here's an image of Ganymede taken with the Hubble Space Telescope and taken with Hale with adaptive optics. And you can see the scale there, 1 arc second. So you can see the detail seen by both telescopes is much better than 1 arc second. But bear in mind, it's not the way round you think. The Hale is actually on the left. Hale with adaptive optics can beat the Hubble Space Telescope. So proving that a 5-meter mirror, if you do it right, is better than a 2.5-meter mirror in space is a very valuable technology proof of principle, if you like. And it's this sort of thing that the Hale excels at. And that is why it is still a very useful research-grade telescope, even now. And if you want it to continue being a research-grade telescope, well, you've got to maintain it. And that means cleaning the mirror every once in a while. So every 18 months to 2 years or so, the mirror comes out and the mirror sidles across and is given a damn good clean because it's been in the Californian atmosphere for a year or two. Basically, you give it a good clean, and then you get a little bit of, once you've washed it down with soap, you get some mild acid, and you spray the acid on the surface, and that takes the aluminium away, and you're left with just the glass. Now you're down to bare glass, you give the glass a damn good cleaning. And then you're finally at the point where you can say, right, I think we've now got the mirror back to its effectively pristine state. And the outer band can then come off. And again, you can now see rather nicely, looking down into the mirror surface or into the side of the mirror, you can see what appears to be solid objects, but remember they're just air gaps because the fire bricks have been removed and you're just left with a rough surface, which is why they look like they are solid objects. But we're looking at a perfectly smooth surface, looking down into the air gaps below with the ribbed structure behind. Once that's been cleaned, it can be taken back into the vacuum tank and given a fresh coat of aluminium, and hopefully it's then good for another couple of years. Yes, it'll need a new lick of paint every once in a while, but it's a workhorse that's been running for 3/4 of a century, and it's been an amazing tool for astronomers, not just for the years that it was the biggest telescope in the world, but even now it is still a useful telescope. So I've been telling you about George Ellery Hale and how he decided on where to put the telescope and how to make the telescope, and I told you a little bit about what it's doing now. Acknowledgements, I've got a lot of information from the Caltech archives. They are wonderful. They're effectively public domain. There's a lot of information about Palomar. There's also a lot of information from the Corning Glass Museum because they are so proud of making the 200-inch mirror that there's a lot of information there as well. Virtually everything I've said this evening is in one of those 4 publications. Either The Glass Giant of Palomar, which makes wonderful reading from the 1930s, or the work of Russell Porter is in his drawings are in these books in the top right and the bottom left. The Hale telescope was the biggest telescope in the world when I was born. It was the biggest telescope in the world for my entire childhood. It was the biggest telescope in the world for most of my adult life, and as I say, was only overtaken in the 1990s. That is testament to the people who thought about the design, the engineers who built it, and above all, to the one man who pulled it all together, George Ellery Hale. Thank you all very much.